Okay, so last week we used this technique called quantifier elimination, and using that we proved that the theory of valid sentences in the empty signature, where you don't have any vocabulary apart from equality, which you always have, so that theory is decidable. So we got a nice computational result from a logical using logical methods, namely showing that a theory enjoyed quantifier elimination. We could eliminate the quantifiers from formulas. And to do that, we couldn't actually do that in the theory of the empty signature itself, of valid sentences over the empty signature, but we extended the signature with these additional propositional constants expressing cardinality constraints, and using that we were able to get the result. This week we're going to see another similar application of quantifier elimination, which we're again going to use to establish the decidability of a theory, of an interesting theory, and to also get some useful properties out of this result. So I'm going to remind you to start with of a result that I asserted in the very first lecture, in setting the background for the perspective on logic we're going to be following during this course. And this is an old result of Tarski, a very important result. From, I think, 1940s, it was published. I'm not sure exactly the year. And this is the theory reals, when we have our signature, the common signature we were looking at in the first two lectures, so the signature of a ring with units, so we have plus and 0 and 1 and multiplication and 1. Is decidable. Of course, the reals are not just a ring, they're a field, and they're not just any field, they're a very important field. For example, they enjoy the property that any polynomial of odd degree has a root, has a 0. Such fields are called real closed fields. There are algebraically closed fields, which enjoy the property that every polynomial has a 0. They're like the complex numbers is an algebraically closed field, like the fundamental theorem of algebra. But reals, obviously not. It's not the case that every polynomial has a root, but every polynomial of odd degree has a root. In fact, this theory, it's the theory of the real numbers, so it's the theory of an individual structure, so it's a complete theory, but it turns out to be also the first order theory of all algebraic, not algebraically closed, but all real closed fields. So any two real closed fields, there are different choices of real closed field one can take, and any two real closed fields have the same first order theory. So this is the theory of real closed fields. And it's an important theory because, as I told you in the first lecture, essentially Euclidean geometry can be encoded. So the geometry of Euclid's Elements book, and much more can be encoded in this theory. So it's very nice. It's decidable. You don't need to do all the proofs in Euclid. You can just pop your statements into a computer, which can compute away and tell you whether or not something's a theorem. something's a fact about geometry or not. In principle, that is, but in practice, it turns out to be rather inefficient. And one can quantify exactly how inefficient it is. Now, this theory was proved to be decidable by Tarski using the technique we used last week. So by establishing quantifier elimination, the Tarski proved decidability via quantifier elimination, just as we did last week. And that leads to a particularly inefficient process, because we discussed the inefficiencies in what we did last week. And one of the inefficiencies was every time we eliminated a quantifier, we had to convert into either conjunctive normal form or disjunctive normal form. So we were particularly using disjunctive normal form to eliminate existential quantifiers. And that leads to, for those of you who know a bit about different complexity classes, that leads to an algorithm of a complexity that's known as non-elementary, which is basically worse than any iterated exponential. So that's a very bad algorithm. But actually, the decidability of this theory is quite useful in practice, and there are more practical algorithms that decide the theory. And there's a very beautiful theory here. So, much better decision. So just to let you know what the buzzword is here. So much better decision procedures something called cylindrical decomposition. I think it's actually called cylindrical algebraic decomposition. And essentially, you view a formula in many variables as defining some geometric figure that actually you can, is basically turns out to be a finite number of a finite number of connected components. And the cylindric decomposition looks at the shapes of these different individual components and breaks them down into pieces of smaller dimensions, very roughly. Okay, so this is a beautiful result. Too much for this course. If you look at the Rautenberg textbook, I think there is a proof of this in the Rautenberg textbook, although it relies on quite a bit of algebra. So you need to know a bit of algebra to understand that proof. So what we're going to do today is like a modest version of this result. So how modest are we going to be?
May I ask, once a proof is discovered with this procedure, can it be verified in a reasonable amount of time as a correct proof afterwards?
Aha.
So practically speaking, if we document what we do, we would only have to state the theorem and discover a proof once, and then everybody else could independently verify it efficiently.
Aha,
that is the case.
Right. Okay, so especially the way these decision procedures work, they don't provide you with, so you put in a first order sentence that you want to know is true or false. They don't tell you a proof of the sentence from some axioms. They basically tell you true or false. And it's done more using semantic methods. I think it would be possible to modify the procedure to get a proof from the axioms for a real closed field, because especially if you follow quantifier elimination, basically every step you do there you can justify in terms of the axioms. So you would be able to, so I'm sure you could do that, and in which case, once you've got the proof, you could verify it in efficient time in the size of the proof. But the problem is the size of the proof would be essentially proportional to the amount of work you did in the quantifier elimination. So I very much doubt there's something useful that can be done with that. But I don't know. I've never thought about that. We'll see people look at the question in that way. Were there other questions? Okay, sorry, I thought I saw another hand. Right, okay, so anyway, we're not going to do this, we're going to do something more modest. So how could one be more modest? Well, a very little thing one could look at, we could just look at the theory of zero and addition in the real numbers. So of course this is decidable because it's just a subsignature of this. We're still looking at the same structure. So any sentence over that signature is a sentence over this signature, and the answer is the same because we're looking at the truth in the real numbers. But it turns out this theory is a very nice one, because this is exactly for those of you who are of an algebraic inclination, this is the theory of something called torsion-free divisible groups. Divisible groups are a kind of abelian group, so it's a form of the theory of torsion-free divisible groups. And so it's kind of nice to have a decision procedure for this theory. There are quite a lot of such groups in practice. Another example of one of such a group is the complex numbers. The theory of addition on the complex numbers. It's the same theory. So this signature is not enough to distinguish between the reals and the complex numbers. Yes?
What precisely do you mean by the same here?
The same theory.
Yes.
Well, we've got the same signature.
Yes.
So we've got exactly the same formulas.
Yes, in terms of sentences.
Yeah.
Sorry.
So the theory, so it's yeah, the same set of
Yes, yes.
sentences in the theory. Okay, so we could go now. As you might imagine, the difficulties here arise from multiplication. So let's at least stick 1 in. This actually doesn't change much, because when you've got 0 and plus, and you put in a constant for 1, you can't really distinguish 1 from, you could have put in a constant for e or pi. It doesn't really matter. You have, at least I think what I'm saying is right. You have isomorphisms that scale, and they turn out to be, they're isomorphisms, so you get the same first order theory back. So this is basically just the theory of torsion-free divisible groups with a distinguished element. Okay, but anyway, that's we're still not distinguishing between the reals and the complex numbers. So this is again the same. One thing we could do that really puts us in the into the reals rather than the complex numbers is add the order. So the fact that the order relation. So the fact that we had the same theory before is a proof that the order relation is not definable if you just have 0 plus and 1. The order relation is definable if you have multiplication. So the order relation is definable here. We did that in the first or second lecture. I don't remember. And this is the theory we're going to look at today. Okay, so we've got everything in here apart from multiplication, but we do have the order, so we know we're not in the complex numbers because one of the true sentences in this theory is going to be the sentence that says that this is a strict linear order, and it's not true that that linear order will enjoy properties that there is no such order on the complex numbers. Okay, so our main theorem today is that this theory is decidable. But actually, to prove this, one can prove that this theory satisfies quantifier elimination and use that to get decidability. So decidability can be proved directly by decidability.
Quantifier.
Sorry, by quantifier elimination. Thank you. Otherwise, it'd be a bit tautologous. By quantifier, quant-elim. But it's a bit fussy doing it just in terms of this theory. So what we're going to do is we're actually going to extend the signature, just like we did last week. But last week we had to extend the signature in order for quantifier elimination to be true. Today we're extending the signature by choice to actually have a language that's more convenient to deal with. And we'll extend it in such a way that lets us see really what kind of thing we're working with, and actually makes it seem a more interesting theory than it just seems when written in this way. So for convenience, we shall use an extended signature. Instead. So last week, our extension of the signature was we started with the empty signature and we added these propositional constants that represented sentences that assert properties of cardinality. The cardinality, we had the constant c greater than or equal to n that state for any number n, we had such a property that was equivalent, we axiomatized it to be equivalent to the sentence that stated the cardinality of the structure is at least n. In this case, what we're going to do is we're going to extend the signature with some function symbols that extend the language with some definable functions that we have. So what does it mean to define a function? So we'll do this in generality first and then look at the special case. So if we've got a theory T over whatever signature, so a theory T is said to define a function, defines a function let's put it like this. In a theory T, a formula A. So remember, formulas express relationships between their free variables, and to define a function that takes n arguments, we use a formula that has n plus 1 free variables, and we say that this formula defines a function if the relationship it asserts between the x's and the y is functional. So for any tuple of x's, there exists a unique y that satisfies the tuple. So we say defines a function if in the theory T, we could, in the theory T, it's a consequence of the theory that this relation is functional. So in other words, it's a consequence of the theory T. Here we're using this double turnstile as entailment. So it follows from the theory T that for all x1 to xn, we want to say there exists a unique y. I mean, you know how to say there exists a unique y, but anyway, let's write it out. There exists a unique y satisfying a x1 to xn to y. And it also proves that any two such y and z are equal. So for all x1 to xn, and for all y and z, if, oops, that should be an A. If y and z are both in the relation with the x's, then y equals z. Okay.
Excuse me.
Yeah.
If I may, a question about notation. So this, in contrast to the previous week, this means that A does have all of these free variables, as opposed to just the free variables being a subset of these ones.
So no, it again means A has at most these three variables. Just if it doesn't mention some of the variables, the function it defines is going to be is going to not depend on that variable. But you know, for a projection function, say the projection function that maps x1 to xn to x1, we could just have the formula. We could just have the formula x1 equals y. And that would define the projection function. We can use that to define the projection.
What about y?
I should say an n-ary function. It has to mention y because otherwise you can't satisfy this condition. Yes. Yeah. Because otherwise this, yeah. So unless T is the theory that says there's only one element of the universe, in which case it also doesn't need to mention y in that case. But that, yeah.
Yeah, the conjunction has a precedence over the implication.
And the conjunction has a precedence over the implication. Yeah, I didn't actually talk about precedent, but that's standard. It's yeah. I never talked about precedence of logical operations. Okay. So in our theory, so consider the formula which is simply an atomic formula where we add m copies of x together and state that this together two free variables. This is a formula defining it as a unary function, a one-argument function. Defines the function in numbers with 0, 1, plus 1, and less than. And what function is this? Somebody must be able to
multiplication by m over n.
Yeah, multiplication by m over n. Yeah, very good. Is that the right way around? Okay, so y equals m over n times x. Yeah, so it's the multiplication. So it's the function r maps to m over n times r. Okay. And what about the function here on this side? This define. So again defines the function, and it defines the function.
Multiplying by minus.
Yeah, by multiplying by minus. So this is r goes to minus m over n times r. Okay. And our new signature is going to be, we add function symbols for these definable functions. So the new signature, the board organization is a little bit complicated here because I'm doing it in a, I want to keep this part for something continuing the general theory here. So I'll just do the specific thing here. So the new signature is for every rational number q, we're going to add a unary constant symbol which represents multiplication by that rational number. So we're adding some scalar multiplications basically, but scalar multiplications by rational numbers. So new signature for every rational q, we still have the old signature, but we include a unary function symbol which I'll just write as q dot, and the point is q dot of x means multiply x by q. That's how we interpret it in the real numbers. Standing for scalar multiplication by q. The reason I'm calling it scalar multiplication is because it's a fixed function symbol for every rational. So we can't use a variable on the left-hand side here. We can't get back full multiplication. So it's kind of analogous to, in a vector space, for example, we have a scalar multiplication where you take the scalar from outside, from the field outside, and you scalar multiply by a vector, which is something from in the vector space. And so the new signature, and so the new theory is the theory of the real numbers for the new signature, which is 0 plus 1 less than, together with the three unary function symbols for every rational number. Are we considering the theory of true sentences there in the real numbers? So in general, there's also a way that we can get to this. So here I'm defining the theory semantically in terms of the real numbers, but there's a way we can get to this second theory from the first without saying, well, it's just the theory by extending the interpretation in the real numbers. And we get that in a systematic way from knowing that every new function symbol that we've added is definable by a formula in the original language. And this is, so in general, and this is a very useful thing one can do in logic, in general, whenever you have a formula that defines a function, you can add a function symbol for that function to the signature and extend the theory with an axiom saying you're defining this function symbol to be the definable function, and you basically get the same theory back again with a slightly richer language for expressing things, and that you've got this nice function symbol that can be quite handy. So when A defines a function, we extend the signature with a new n-ary function. So we're finding a function in n arguments with a new n-ary function symbol f. Well, let's call it f new. And we extend the theory T by adding a new axiom to T. Extend T by adding the axiom that says that f new defines the function defined by A. F new stands for the function defined by A. By adding, so to say that, we simply need to say for all x1 to xn and y, just for xn, A holds for x1, xn, x1 up to xn, together with the new term we've got, f new of x1 to xn. Okay. That's all we need to say, because we already know the assumption is that the formula A is defining a function, so has a functional behavior. So it's enough just to say that it is in this relation, and then it's forced to be the value of f new on x1 to xn is forced to be the unique value that it can be. And in the notes, in the LaTeX notes, there's some sort of systematic treatment of this extension. Once again, I'm going to skip a little bit the systematic treatment. One of the interesting things is that in this extended theory, any formula in the extended theory can be translated to, you can find an equivalent formula in the original signature. So for any formula in the extended signature, you can find an equivalent formula in the original signature. Moreover, there's an algorithm that gets you that original formula. Essentially, you take a formula in the new signature that might involve the new function symbol, and every time you find the new function symbol, you stick a variable in, you put in a new variable for this term, and you go and you put in a side clause in the formula saying, by the way, that new variable has to be in this A relation with the arguments of the function. So it sounds maybe not too complicated in theory, but if you actually write it's a good exercise to write this out in practice, because it's actually quite subtle to get this exactly right. And I don't want to waste a lot of time in the lecture on it, so I'm not going to. But the principle is important to understand, that we have this new signature that's quite convenient because we have these function symbols, but in principle, we don't need them, because anything we can say using the new function symbols, we could say without them by having kind of larger formulas that use the relation that's defining use the formula that's defining the function symbol. Okay, so we've got, we're writing these. One of the nice things about doing this is that it turns out that terms and equation and atomic formulas in this extended theory have can always be put in a nice normal form. So let me So let me give an example of that. Terms such as so what have we got for terms? Well, of course, we've got variables, because we always have variables. And terms are built up by variables, constants, and function symbols. So for constants and function symbols, we've got variables, we've got 0, 1, we've got addition, and we've got this scalar multiplication. And this is a less than is, of course, a relation symbol, not a function symbol, so it doesn't come into terms. So an example of a term would be something like a half times a quarter times x. So I'm just, this is apply this function symbol to x, but yeah, I'm not putting the brackets in because it's easier to read if I don't. Say plus a quarter times y plus an eighth times 1. But you can always then put this in a normal form, and we would write this, and we write this in a normal form, which I'm just going to write this as in the standard way. So an eighth x plus a quarter y plus an eighth. This is a 1 here. So the point is the general normal form or a term with variables x1 to xn x1 to xn is just simply every term is basically equivalent to a linear combination of variables. Because if you've got iterated applications of the scalar multiplications, of course, they're equivalent to just a single scalar multiplication. So every term has a normal form. So Q1, we only need one scalar multiple of x1 all the way through to one scalar multiple of xn plus some constant q. And I just write it like this, as one normally would, and it's very easy to convert that back to, here this is really q times 1, for example. Okay. And we'll come back to the normal form a little bit later, but these normal forms, having these normal forms is really the convenient reason that we wanted. Well, actually, now we'll see later exactly what the reason that it's useful for having these linear expressions. But basically, every term is a linear expression, and so because of this, I call this, but it's not a standard. Not standard terminology. I don't think there is really standard terminology. I call this the theory of rational linear expressions. In short, RLE. Okay. And the main theorem that we'll prove in the next hour is theorem 1 is that RLE enjoys quantifier elimination from that, we get theorem 2, which is that RLE is decidable. Right, so it's 3 minutes to 5 by the clock on the back wall. So by the clock on the back wall, our official timekeeper will start at 12 minutes past 5. Okay. Okay, so the main theory we're looking at then is this theory of what's a bit of pen, rational linear expressions, theory of the real numbers over the signature where we have addition, constant 1, the less than relation, and these multiplication by work for us. Theorem 1, which is that RLE enjoys quantifier elimination. Fill in. And we're going to prove it by the same method we used last time. So we had this lemma last time. So we're going to recall the lemma. If and only if quantifiers are eliminable. In fact, there was only, well, basically we could reduce quantifier elimination to eliminating the existential quantifier from a formula of a particular form. So if and only if the existential quantifier, but let's say quantifiers are eliminable from formulas of the form, there's an existential statement over a conjunction of literals. Okay, literals, where, well, I forgot this when I first wrote the lemma, but we added it later, where the variable x appears in all the, where x appears in every literal Li. But in fact, what we're going to use now is a stronger version of this, which is actually a very simple modification. That is actually enough to restrict to quantify to conjunctions of literals of a certain kind. If we have a distinguished, we might have a distinguished collection of sufficient literals to look at. So I'm going to call such a thing a literal base. So x appears in every literal xi, and every Li belongs to the chosen literal base. It's the same literal base for everything. So a literal base is a collection of literals that are sufficient to look at. We don't need to. So the problem we've got now is we've got we've got a less than and we've got equality, and so we've got 4 different kinds of literals. And if we consider existential quantifications with combinations of all these 4 different kinds of literals, things get complicated. So it's nice to be able to reduce the literals that we need to consider in these existential quantifications. So what a literal base is, so a literal base is a collection curly L that's a curly capital L of literals, such that every literal over the signature is equivalent to a combination of literals from literal base L, symmetric L, using only conjunctions and disjunctions. It's best to explain with an example. For example, literals of the form equalities and inequalities form a literal base for the theory of rational linear expressions. Form a literal base for the theory of rational linear expressions. So to see that, very simple. I'm really struggling to find a good pen. I have to go to the reception in the next break. So to show that these form a literal base, we just need to show that every literal over the signature is equivalent in the theory RLE to combinations of these two using combinations using conjunctions and disjunctions. So here we've got equalities and strict inequalities. So these are actually the atomic formulas. Literals are, you will recall, atomic formulas and their negations. So we need to show that the negations, so the only other two literals are two forms of literal are the negations. So we just need to show that the negations are definable using conjunctions and disjunctions from literals of this form. So this is because so the negation of an equality, that's equivalent to, so what's a combination of literals of this form that using either conjunctions or disjunctions or both that gives us linear order because we're in the real numbers. So if they're not equal, that's the same as one of them being smaller than the other because we've got a linear order. And T1 is not less than T2. That's equivalent in the theory to
T1 is T2 or T2.
T1 is T2 or, again, because we've got some linear order. Okay, so that's very easy. And then that means, so by this lemma, it's enough for us to prove quantifier elimination to eliminate quantifiers from these existential quantifiers from existential formulas where every one of these literals is either an equality or a strict less than. Okay. So how does one prove? So that was recalling the lemma, but now we've modified the lemma. It's a slight strengthening of the lemma from last week. Basically, the proof of this is the same as the proof of the original lemma. You just check it goes through for a literal base. And as a preliminary to that, one can strengthen negation normal form, conjunctive normal form, and disjunctive normal form. That in all cases, the normal form involves conjunctions and disjunctions of literals from the literal base. Okay, so all those results strengthen with the same proofs. Essentially, you just have to replace literals with the combinations from literal base. So strengthen to results about literals from a literal base. So I'm not going to go through those proofs again, but we'll just work with the lemma as it is. Okay. So, any questions on that while I'm moving forward? Okay, so we want to prove quantifier elimination for rational linear expressions. The conjunction of k literals where every Li contains x and is either an equality or a strict less than, because that's what our literal base is, and is either less than or is one of those forms. However, we're going to simplify this a little bit further now. Base that it's very useful to have these rational linear expressions. So in fact, it suffices to consider Li in the form, in one of the forms, every Li is in one of the forms either some Ti is less than X, so some Ti, or X is less than Ti, where Ti does not contain X. Okay, so we start off with an inequality between two terms or an equality between two terms, and we manipulate it so we get an inequality or an equality that has just X on one side and a term not involving X on the other. And basically this is just high school algebra to do this. Because we've got the rational linear expressions, we can use ordinary algebra to get X on one side and everything else on the other side. So I'm not going to prove that. I'll just give you an example just to so let's do it here. So an example. Suppose we have, and I'm just going to use the one I prepared before. So suppose we had a third times y. We can anyway consider the terms to be in the normal form we considered earlier. So suppose we've got a third times y plus minus a fifth times x. times z plus 2, which is of course 1 plus 1. Oh, but anyway, this is all, which is 2 times the rational multiplication of 1. That's a canonical way of looking at that. Then you just do a bit of algebra. This is equivalent to, and you find out that this is equivalent to, or probably one of you can do it in your head, but anyway, it turns out to be 20 over 27 times y minus 10 over 9, which is of course plus minus 9 minus times the way of encoding minus 40 over 9 is less than x. Anyway, that's one relatively simple example, but I guess it's hopefully obvious to everyone now that we can do this algebra and rearrange the inequalities. Of course, sometimes there's only one subtlety. Sometimes in doing this, you might have x on both sides to start with, and it might cancel out. But if it does cancel out, then you no longer, that's fine, it cancelled out. You no longer have x, you have an equivalent literal in the literal base, and you no longer have x in the remaining literal because it cancelled out. And then you can pull that literal outside the existential quantifier. And so still, for eliminating the existential quantifier, it's enough to consider literals in these 3 forms. Okay? So now we have, again, 2 cases. Case where the literals are, there are these 3 possibilities for the literals. Okay. So case 1, and this is very similar to last week. Case 1 is one of the literals is an equality. 1 Li is an equality. And once again, let's just assume it's L1, because it doesn't matter what order we put them. So say it's L1. X equals T1, where T1 does not contain X. What is the equivalent formula that has no, then the equivalent quantifier-free formula is, okay, can somebody tell me what the equivalent quantifier-free formula is here? The same thing we did last week. Exactly the same thing works. So we take L2 and up to LK, and we substitute T1 for X. Okay, so that's the easy case. You might remember from last week with the theory of finite cardinal bounds. That was again the easy case, and then the other case where we don't have any equality was much more complicated. So case 2 is the complicated case here. And let me just see. Right. I just want to be consistent with my notes. So otherwise, we don't have any equalities. So we have 2 possible literal forms. We either have literal forms where some terms are less than x, and we have literals where some terms are greater than x. So in that case, then and we've got some number of conjunctions where the terms are less than x. So I'm going to call these terms s actually. So we've got, suppose there are m of these, and we've got some other number of some number of conjunctions of terms being bigger than x. So x is less than t1 and x is less than tn. Say. Okay. Terms, the rational linear expressions in variables different from x. We've got a statement that a bunch of them are less than x and a bunch of them are greater than x. And we want to express the statement there exists some x that's bigger than all the s terms and smaller than all the t terms, using a formula that doesn't involve a quantifier. So can anyone see how to do that? One would suggest that we say that the max of the S1 to Sm, the maximum of these is less than the minimum of these. But you can't really express that without using quantifiers. So if you want to say that the z that is the larger of the, so you can't easily do it like that. But the right way to do it is exactly what you said. So the right way to do it is just say all the s's are less than all the t's. So it's just, again, a double conjunction. But notice this is much more efficient than what we did last week. Last week we had this big conjunction over all partitions of n variables, which was a horrible thing to consider. In this case, this is just quadratic in the, actually the formula size, the formula size is quadratic in the size of this formula. Because, we need to pair off every s against every t. So it's just the conjunction from I is 1 to m, and conjunction from j is 1 to n, of si is less than tj. Okay, and we're done. So that is quantifier elimination for the theory. We can show that the theory is decidable. So this is theorem 2 now. The theory of rational linear expressions is decidable. And so remember, decidability means we can find an algorithm that inputs sentences, takes a sentence over the signature as its input, and will tell us either true if the sentence belongs to the theory, and false if the sentence does not belong to the theory. Unlike last week, so last week we had a theory that's not complete, which is the theory of valid sentences over the empty signature. So for example, the formula saying the cardinality is at least 3 is not valid because there are models whose cardinality is less than 3. But also its negation is also not valid because there are models whose cardinality is greater than or equal to 3. So that's a formula, neither it nor its negation belong to the theory. In this case, the theory is complete. Why is the theory complete? Or its negations in the theory. Sentence explanation for why the theory is complete.
If you use the algorithm on a sentence, you always get an output.
Oh, okay. Well, that's an answer once we've given the algorithm, yes, and that will be true. But we will always get an output anyway. But the point is, say, does a sentence belong to the theory or not? So it will always give an output. But in fact, the algorithm, we can see the algorithm will always give us true for either one sentence or its negation. Maybe that's what you mean. But there's just a reason this theory, rational linear expressions, is defined as the theory of the real number, the theory of true sentences in the real numbers. We're interpreting it in a particular structure. So because it's the theory of an individual structure, it is complete. In that model, it's a theory of a single model, and so a sentence is either true or false in the model, and if it's false, its negation is true. So that's the short reason why it's complete. Right. So it's a complete theory. The input to the algorithm is a sentence, and we need to, given a sentence, we need to give an algorithm for deciding whether or not it's true or false in the real number. So given a sentence, A as input, I mean, the first thing we notice is the proof that we have quantifier elimination gives us an algorithm for, just like last week, an algorithm for converting the formula to an equivalent quantifier-free formula. So we follow. It's again, even though this step is actually is quite a bit more efficient than last week, it's still an inefficient algorithm because the algorithm still relies on, at every quantifier elimination step, putting the formula into disjunctive normal form. So it's still a very inefficient algorithm, but we apply quantifier elimination algorithmically to obtain quantifier-free formula that's equivalent to A. So in this case, what do quantifier-free formulas look like? So last week, quantifier-free formulas were quite simple because we just had, we only had the only atomic formulas we had that contained no variables were these propositional constants for cardinality. And so the literals were either those or their negation. In this case, we've got equalities and less thans between terms, and the terms are now more complicated. The terms are these rational linear expressions. However, we're looking at terms with no free variables, well, with no variables, and any rational linear expression with no variables is equivalent to just a rational number, is equal to a rational number. Okay. Which is a Boolean combination. So again, by that I mean combination of atomic formulas under the propositional connectives. A Boolean combination of where T1 and T2 are closed terms. So closed term, this means the term has no variables. So it's just formed from constants and function symbols. A closed term, so this means term has no variables. So every closed term is computably, as I said, it's a rational linear expression where you only have constants and you don't have variables, and you can compute exactly with rational numbers. So every closed term is computably equal to a rational number. So I'm sorry, I'm switching to red because the black and blue pens just don't seem to work very well. I need to go to get replacements. So every closed term can be algorithmically algorithmically. It just means there's an easy algorithm to compute it. Computable. It's a bit of what's the word for saying the same thing twice? I mean, computable is also kind of has algorithmic implicit in it. Anyway, so every closed term is computable to a rational number. And so we basically the equalities of the form Q1 equals Q2, and the inequalities are Q1 less than Q2. And we've got two rational numbers here and here given, but in each case by a numerator and denominator, and we need to test if they're equal or if they're less than. And of course, those are obviously computable tests that one can do very easily. And we've simply got a Boolean, so each of these computes to a truth value, and then we've got a Boolean combination of truth values, and you simply use the truth table definitions of the logical connectives to compute the resulting truth value. So each of these, so each atomic formula computes to true or false, and hence algorithm, because the algorithm returns true if it computes to true and false if it returns to false. And coming back to why the theory is complete, so actually your way of answering the question, if we view this algorithm as an algorithm that computes a truth value for a sentence, which is a perfectly legitimate interpretation of it, we also see just from this algorithm that the theory is complete. So I think that's the point you were making. Right, it's very early for the break, but there is a pen emergency, and I don't have a full hour of material for the last hour anyway. So I suggest we have an early break now. I should go and get some, hopefully some pens from reception, and we'll start. It's 1:45 by the clock on the back wall, so we start again at 6 o'clock. Are there any questions? No. Right. Good. Okay, so RLE, rational linear expressions, is the theory of the real numbers, and we've got the signature all these rational multiplications. The theory of rational linear expressions. As I said, because it's the theory of a single structure, the real numbers, then for that very reason, every sentence is either, if we were just asking, is it true in the real numbers or false in the real numbers? So it's either in the theory or not. And the proof of decidability showed that we we can, from the sentence, we can compute the truth value of, yeah, it's either true in the reals or false in the reals. So that's for sentences. It's interesting to ask, what does quantifier elimination tell us about what a general formula can say? So a general formula will have some number of free variables, n free variables say, and the formula expresses a relationship between those variables. In other words, it expresses a subset of R to the n. So it's a collection of points in n-dimensional Euclidean space, and so a formula is basically defining some geometric figure. And the key to understanding what formulas can express, actually the really crucial point occurs already in dimension 1. And we're going to show that formulas in dimension 1 have a very limited expressivity, so formulas in one free variable. And then it turns out that in cases in which that holds, many consequences follow from the property that such formulas are of limited expressivity. But before talking about that, let's just look at what such formulas say and what the limit in the expressivity is. So we're going to consider, so somehow the question is, we can ask which subsets of the real numbers can we define by a formula A with one free variable x. So any such formula defines the set those real numbers such that A holds in the structure of the real numbers. It seems this my new pens are no better than the old pens. Yeah, so I don't know how many of you know, Silver, the receptionist, retired about 2 or 3 weeks ago. The reception seems to be less open than it used to be. That's just my. So I went down to the reception to get new pens, and there was nobody at reception, so I couldn't get new pens from there. So in the end, I raided a classroom upstairs. I tried to go into one where Sasha Speglet was teaching and got a very hard glare from him when I opened the door. But anyway, I found an empty classroom and I raided some pens from there, but they don't actually seem to be very good. Anyway, so the formula defines, so one way of defining it would be those real numbers such that A holds, this is better, if we interpret under the environment where we map, we interpret the free variable of A, x as R. Oh, wonderful, thank you. But this one looks like it will last for a while, but thank you very much. But normally we would write this in the less fussy way like this. So we mix syntax and semantics, and we say that the formula A holds for the value R from the real numbers. Okay. Any such formula defines this set. Does anyone have a guess at what the collection of sets we can define in such a way is? For the set we can't define. We can't define the set of integers, for example, as a subset of the reals.
Well, the sets would be finite because there are finitely many variables, right?
Well, the sets won't be finite because we could, I mean, for example, with the formula true, we have the whole set of real numbers. That's not a finite set. Oh, yeah.
We couldn't do the Vitali construction.
Sorry?
We couldn't do the Vitali construction.
We also couldn't do the Vitali construction. We definitely couldn't do that. Can't even define that in set theory unless you have without something like the axiom of choice to help you. Even so, you can't define it as a formula. because we can't specify it uniquely. Anyway, this is the definition of definable set. It actually turns out it's more interesting to consider a slightly more permissive definition, which is a set definable in parameters. So this is definable by a formula in one variable, but we say a subset. So we're going to look at a formula with the variable x that we're thinking of as we want to define a subset in x, and parameter variables z1 through to zk defines in parameters a1 to ak. So these are real numbers. The set. So we're going to have the more general notion of defining the set of real numbers are such that in the real numbers it's true, the formula A is true for R, where the values of the variables z1 to zk are always fixed in these parameters. So that may seem a little bit abstract, but as an example, the half-open interval from minus e, where e is Euler's number, of course, to pi. So it's a half-open interval, so we'll close it at that end, is definable in parameters. So we give e and pi as parameters by the formula A, which has x for the elements we're defining it, and two parameters z1 and z2, which we're giving it e and pi, and it's definable by the formula minus z1 is less than x, and x is less than z2, or x is equal to z2. Okay, so that's definable in parameters. To classify exactly the subsets that are definable in parameters. So the point of the parameters is just that it allows us to give ourselves any finite number of real numbers that we can use as, for example, as endpoints of things, or as we're doing here. Because in the language itself, we obviously, I mean, it's not maybe totally obvious, but well, we certainly can't define numbers like pi and e in the language that we've got, which is very rational. So the theorem is the following are equivalent for a subset, let's say x of the real numbers. So the first one is x is definable in parameters in theory of rational linear expressions, so in the language that we've got. And the second one tells us exactly what these subsets are. So let me offer you the chance to make a suggestion again. We've seen an example here, a half-open interval. We could, of course, strictify this equality and make it an open interval, or we could non-strictify this equality and make it a closed interval. Any ideas?
Unions and intersections of open and closed intervals and
okay.
How do you say product?
So the intersection of two intervals is again an interval. So maybe we don't need the intersections there. So indeed, unions of intervals. Where interval could be an open interval, a closed interval, or a half open or a half open interval. And an interval also includes the whole real numbers is an interval, or the positive reals is an interval. But it's finite unions of intervals. So X is a finite union of intervals. So the precise definition of interval is X is an interval if if you've got two elements of X and A is strictly less than B, implies that then the open interval from A to B is a subset of X. Okay, so if you contain 1 point less than the other, everything between it is also contained within the interval. Okay, so it's quite easy that finite union of intervals are definable, because you basically use this trick for any interval. You might have one endpoint if it goes off to infinity, or you might have two, but it doesn't matter. You just do something similar to define the interval, and then you just use finite disjunction of so many things, giving all the relevant endpoints as parameters. So it's easy to show that 2 implies 1. So why does 1 imply 2? And of course, this is a consequence of quantifier elimination. So I don't want to give the full proof because it's a bit fussy, but let's just do the idea. Proof idea. So suppose we've got some formula, some complicated formula in parameter with variable x, which is the real number that we're putting in the set, and z1 to zk, which is specifying the parameters. So I suppose this defines x in parameters by quantifier elimination. A is equivalent to a quantifier-free formula, and by disjunctive normal form, it's equivalent to a quantifier-free formula in disjunctive normal form. So rather than being tedious about it and giving names to all these formulas, let's just say by quantifier elimination, we can assume that A is a finite disjunction of conjunctions of literals. So by quantifier elimination, A is a finite disjunction. So this is disjunctive normal form of conjunctions of literals. And by what we did earlier about the literal base, we can assume those literals are either strict inequalities or equalities. The literals of the form term is a rational. Every term is a rational linear expression in x through to in variables x through to z1 through to zk. But we're actually just interested in the z1 and zk. They're just variables that stand for these parameters a1 to ak. So we can plug those values a1 to ak in for the z1 to zk. We don't have a term in our language anymore because we're just plugging real number values in. But still, we can think what the linear expression looks like for those values. So plugging in values okay for z1 to zk, every term is equivalent to some real number r plus some real number s, say, times x. We don't necessarily have, but the term with the multiple of s can always be irrational, actually. The parameters can't come into, the only way we've got to manipulating an x is by multiplying it by rational numbers. We can't put in parameter variables into the same part of the expression. So r is a real number and q is a rational number. So we have a finite disjunction of conjunctions of strict inequalities and equalities of this form. And it is not hard. So then, once again, we can rearrange all these inequalities and equalities. So you have x on one side and a real number on the other. So every literal t1 less than t2 or t1 equals t2 has the form is equivalent to one of the form either x is less than r, x equals r, or r is less than x. And so we've got a disjunction of conjunctions of these things, and it's easy to see that those define. So we've got a finite disjunction that gives us the finite union, and it's easy to see the conjunctions define either the empty set or intervals. Well, the empty set is actually trivially an interval by this definition here. So it is easy to see a conjunction of such literals defines an interval. So since we've got a finite disjunction of such things, we get a finite union of intervals. So that's, I think, enough for the idea. So there's a kind of very limited expressivity of formulas in one variable, even if we go to the extra step of allowing ourselves to use parameters that can be arbitrary real numbers. Okay? And this property turns out to be very important. It has a name, it's called O-minimality. And what's surprising is that O-minimality, so this theorem here, I'll just rub off the top of this board. So what we've shown, the theorem says RLE is O-minim. And remember, rational linear expressions is equivalent because we obtained, we extended our original theory by adding these multiplications by a rational constant. But those were already definable by formulas. So also, because it was basically equivalent to it, also the theory of real numbers, what we started with, the theory we started with plus 0, 1, not multiplication, but the less than relation, is also minimal. And also decidable, because it's equivalent to the theory of rational linear expressions, minimal. It in expressivity. But surprisingly, this property actually persists, even if we expand the language here. So the theory that I mentioned right at the beginning, Tarski's theory, the theory of real closed fields, so where we have also multiplication, and we don't need the less than. This is also minimal. So once again, even if we add multiplication, we can't define, for example, the integers. Notice a singleton is an interval by this definition. So we can define any finite union of singletons, but we can't define the integers as an infinite union of singletons, a very special one. So this is minimal. And in fact, if we could define the integers, it would turn out this could not be decidable because the theory of true arithmetic, which we're going to look at later in the course, would be reducible to this. Theory if we could extract the integers. But so this was, this is a consequence of Tarski's proof of quantifier elimination that I alluded to as a bit too complicated for this course. But still a very nice result. A very celebrated result from the 1990s is that even we take this famous theory, Tarski's theory, and we extend it with also the exponential function e to the power of x, this is still minimal. Called Wilke's theorem. About this machinery, this minimal property, it might seem like a strong limitation. You can only define in parameters finite unions of intervals. But there's a more positive way of looking at it, which is if one wants to do geometry in n dimensions, well, geometry, there's no reason for geometry in the classic sense of the word to consider infinite unions of things. We tend to be interested in sort of finite shapes and finite collections of finite shapes. And so, as I said, Euclidean geometry can be translated into this theory. And actually, this theory, it gives you, so the exponential function, you can also then, of course, define logarithms from it, and you put in some quite interesting functions. You can't get sine and you can't put sine and cosine in because they would be able to define the integers. In the parameter pi, you'd be able to extract the integers from that. But this theory, the fact that it's minimality, what minimality gives you, I mentioned right at the start. Well, I don't remember when I mentioned, but I mentioned at some point an improved algorithm for quantifier elimination, which is called the cylindrical decomposition, where you look at the geometry of definable n-dimensional shapes, and you can decompose them into sort of simpler pieces. So the very simple base case of that is in one dimension. We're decomposing any definable shape into a finite union of intervals. In higher dimensions, it's necessarily much more complicated, but the O minimality is strong enough property to give us a form of what's called cylindrical decomposability. And this turns out to be a very powerful tool. And with this result, this was a very celebrated result of O minimality, this proof of O minimality here. Actually, some open questions in number theory have been resolved as a consequence of this structure. So there's a very nice body of work stemming basically from the late 80s and early and the 1990s. It's still very active up to the present day. That basically, I mean, this is a very, very simple case that basically builds on these ideas of that the only one-dimensional sets you can define are the finite unions of intervals. Okay, so to end with, I want to just consider something that very strongly distinguishes this theory that we've been considering today from these two other theories. And that is, these are the two theories. Well, okay, so the theory we've got today, we've defined it, we've got a signature, rational linear expressions, and we have, and the theory is those true sentences that are true in the real numbers. It actually turns out there's another very natural model of this theory, not the real numbers. Somebody already asked this as a question earlier, privately, but somebody else, can anyone guess what the other natural model is? The natural countable model. They can't be the natural numbers because we can multiply by any rational number. But it's the rational numbers. So Q is also, the rational numbers is also a model of theory. Well, let's just call it RLE, rational linear expressions. But it doesn't matter if we've got the rational multiplications or not. The rationals are not a model of this theory because you can express, you have a simple sentence saying there exists a square root of 2 in this theory, and then there's no error. There is a very natural countable model of this theory too, the set of algebraic numbers, as they're called. Okay, that's a model of this theory. And so it's also a model of this theory. But in this case, we also have the rationals are a model. So how do we prove that the rationals are a model of this theory? Well, what we prove
Не видим. А ти реку думам да враше ти.
Jaz ga nimam. Sem ga pač zanj iskala, pa ga ni bilo dol.
Aš je zihran.
Kaj?
the theorem.
Ja, verjetno ga je Veronika s sabo vzela. Pa Veronika
Any
ima iPhona.
formula well, it doesn't matter. It's a formula, so it's got some it's not just sentence. It's not just a sentence. A of RLE. So then a formula over the signature. I'm not saying it's a sentence that's true in the theory, but just a formula over the signature. It holds that and any environment rho interpreting variables as rational numbers. So any rational environment, it holds that the formula is true in the rational numbers under row if and only if it's true in the real numbers under row. You might think, well, this doesn't look very hard. Let's just prove it. The satisfaction relation is defined by induction on the structure of the formula. Let's just prove it by induction on the structure of the formula. However, you then get stuck when you get to quantifiers, because on this side you're quantifying over a real number, and on this side you're quantifying over a rational number. And who's going to say that if you're trying to satisfy an existential quantifier, who's going to say that if there exists a rational number, that, if there exists a real number that satisfies the property, who's going to say that there also needs to exist a rational number? I mean, that's non-trivial. So it doesn't work to prove it by induction, immediate induction on the structure of formulas. What does work is to use quantifier elimination. So the proof uses quantifier elimination. So because the real numbers have quantifier elimination, actually we don't need to consider formulas with quantifiers in at all. It's just enough to consider quantifier-free formulas here. And it's obvious for quantifier-free formulas that this holds, that this property holds. The problem is, this side we also need Q. We also need the theory to have quantifier elimination over Q. And moreover, we need to know that the same quantifier-free formula works in both cases. So the way I have of proving this result is very, very tedious. You repeat the argument for quantifier elimination in Q and notice that all the same steps work. I mean, it's not tedious because it's easy. We've got the proof already written down and you just check. Every step we did in the reals works in Q and then the result follows. But if any of you are clever enough to be able to find a nice conceptual reason for this, a better way of proving this result, I'd be very interested to hear an argument for it. But anyway, the result holds and it uses, so the proof uses quantifier elimination, and basically we prove that the same quantifier elimination steps work for the theory over the real number, over the rational numbers. Here, this if and only if, saying that a formula holds for the rational numbers if and only if it holds for the real numbers, and this holds for any formula with free variables, as long as we interpret the free variables in the rational numbers, which is necessary in order for the left-hand property to even make sense. It's necessary that we interpret in the rational numbers. So this property star, or rather, that for any, well, this whole property here, let's call the whole thing star. This is stating a very nice property the inclusion function. So it's basically a property of the inclusion function of the rationals into the real numbers. Under the inclusion function, this inclusion function maps true statements about the rationals to true statements about reals, and also vice versa. If you map onto a true statement about the real, you get the true statement about the rationals. And this property of a function between structures, preserving and reflecting proper formulas, is very important in logic, and we're going to come to this in a few lectures' time. It's a very important relation in the subject of what's called model theory, and it says that this inclusion function from the rationals to the reals is something called an elementary embedding. And essentially, this is saying that first order properties in parameters cannot distinguish between these two structures. Okay. So this will be important later in the course. That's everything that I wanted to say today. Are there any questions?
Sorry, could you repeat in what sense properties are meant from Q to R under the function?
So A is a formula, so it states a property, and we need an environment interpreting the free variables, but that's the same thing as plugging in rational parameters into A for the variables. And whenever we plug into rational, then A is true as a property of rational numbers, if and only if it's true as a property of real numbers. But more generally, if we have any function between structures, we can ask for, does an environment, if we interpret the parameters as in this structure, if we map those parameters under the function into the other structure, does it hold that the truth of the formula is preserved and reflected? And in fact, it turns out that preservation of truth is enough for reflection of truth, because if you preserve all properties from left to right, you also preserve the negation. So by the contrapositive, you reflect them. So this turns out to be really important for relating structures. When is it the case that your function mapping between structures preserves first order logical properties? And that's this concept of elementary embedding, which will be important later. Does that answer the question? Yeah. Any other? Okay, so I guess that's it. But actually, just one comment on elementary embeddings, given that you asked. So elementary embeddings actually form an example of a category with a very nice structure. So you could, those who are interested in categories, categories of elementary embeddings are very interesting things to look at. I was going to say what the structure is, but then I realised it's so long ago that I last thought about this, that I'll probably get it wrong. And I don't want to say it on the video. So anyway, but there is some nice category theory there. Oh, anyway, that's it.